Hello all. So this is the video solution for the third homework question on the second classical mechanics homework. So part A of this problem wants us to draw a force diagram for a rocket after launch. So in this scenario, we're going to assume that its boosters are still providing thrust, therefore a force. And if we make that assumption, then we have three separate forces acting on our rocket. The first one and the only one in the upwards direction is the force of the boosters or the force of the thrusters. And then we have two forces opposing that force. We have gravity, which always points down. And then we have the drag caused by the air resistance of the rocket, pointing downwards as well. This is because the rocket is moving in an upwards direction, and drag has to oppose the direction of motion. Using this force diagram, I can write an equation for my net force, which is simply the sum of my three forces: the force from the boosters, the force from gravity, and the force from air resistance. So the second part of this question asks you to calculate the net acceleration of the rocket. You do this using Newton's second law. So you know that the net force is equal to the net acceleration times mass. And since gravity, drag, and the boosters are only acting in the y direction, we can rewrite this into just components, saying that the net force in the y direction is simply the mass times the net acceleration in the y direction. And then I can rewrite my net force using this equation as the force of the boosters plus the force due to gravity. Note that I'm not including drag here because we're not given any information about the drag coefficient. So it's probably easier just to assume for this problem that there is no air resistance. So using this equation here, I can solve for the acceleration simply by dividing this net force equation by m. And doing so gets me this equation. I know that the force of gravity is equal to negative mg, so I can plug that in. And then I'm given values for the force of the boosters and the mass. Little g is a constant. So plugging in all those numbers and solving gives you an acceleration of 7.7 meters per second squared. Note that because that acceleration is positive, that means that the net force in the y direction is pointing up, which means the rocket is accelerating upwards, which makes sense for this problem. Whenever you're solving for a value of a problem like this, we can kind of visualize it. See if the numerical answer you get makes sense. So having a positive acceleration here makes sense because our rocket should be accelerating upwards. And so the last part of this problem wants you to calculate the velocity of the rocket at 20 seconds using the acceleration you found previously. So assuming that this acceleration is constant throughout at least those 20 seconds, we can say that the velocity at 20 seconds is equal to the integral of acceleration with respect to time from the initial time, which I'm going to say is 0 seconds, to 20 seconds. And so since I know what acceleration is from the previous part, I can simply plug that in. The integral of a constant is just that constant times t, so 7.7 times t from 0 to 20. Using the fundamental theorem of calculus, that's 7.7 times 20 minus 7.7 times 0, which gives you a total velocity at the end of 159 meters per second, again, assuming that that acceleration is constant. So I hope this cleared up any questions you may have, and please let Morten, Jeremy, or I know if you need any other help.